The moon looks peaceful from Earth, but it hides a treacherous reality most people don't know about. Our celestial neighbor might seem calm and serene, yet it contains some of our solar system's most dangerous environments. The South Pole-Aitken Basin, the moon's largest crater, stretches several miles below the surface. Dark side mysteries, extreme radiation exposure, and violent moonquakes make the lunar landscape particularly hazardous. These deep craters create unique challenges that future explorers must overcome. This piece will take you through the moon's fascinating mysteries. You'll learn about its volcanic past, radiation dangers, and seismic activities that make certain regions risky. We'll also break down how these obstacles affect future colonization plans, and what they mean for human survival on our cosmic companion. Ancient volcanic activity on the moon. The ancient volcanic mysteries of the moon tell a more dynamic story than we once thought. Recent findings have changed what we know about lunar volcanic activity. Scientists now know the moon stayed volcanically active much longer than they first believed. Historical evidence of lunar volcanism. Volcanic activity on the moon spans an incredible timeline. The most intense period happened between 3.8 and 3.1 billion years ago. Scientists found evidence through the Chang'e 5 mission that showed volcanic activity existed just 120 million years ago. This matches Earth's Cretaceous period when dinosaurs roamed our planet. Lava plains and basalt deposits. The moon's volcanic legacy shows up best in its vast mare, dark plains that cover about 16% of the lunar surface. These big basaltic plains have several volcanic features, sinuous rills that stretch up to 566 kilometers. Volcanic glass beads that formed from ancient magma fountains, lava tubes that could become future lunar bases. Scientists found these volcanic features spread unevenly across the moon. The near side has substantially more volcanic deposits than the far side. Oceanus Procellarum holds nearly half of all known sinuous rills. Current volcanic risk assessment scientists found lots of past volcanic activity, but the moon shows no signs of active volcanism today. The discovery of young volcanic deposits gives us new insights into lunar geology. The Lunar Reconnaissance Orbiter spotted 70 irregular mare patches on the moon's near side. This suggests volcanic activity slowed down gradually instead of stopping suddenly. These findings made scientists rethink the moon's thermal history. Young volcanic features show parts of the lunar mantle stayed hot enough to make magma longer than expected. This knowledge is vital as we plan future lunar missions and possible colonization efforts. The volcanic history shows us that while the moon looks unchanging from Earth, it went through big geological changes. Scientists found volcanic glass beads just 123 million years old. This represents some of the youngest confirmed volcanic activity on the moon and challenges previous models of lunar thermal evolution. Radiation exposure. Threats. Scientists face one of their biggest challenges with radiation exposure while learning about the moon's mysteries. Measurements show a shocking truth. Astronauts on the lunar surface get radiation doses about 200 times higher than Earth levels. Solar and cosmic radiation. Two main sources of radiation threaten lunar explorers. Galactic cosmic rays, GCR, from deep space make up about 75% of total radiation exposure solar particle events, SPEs, that trigger sudden radiation spikes. The moon's lack of natural protection makes these radiation sources dangerous. Earth has a magnetic field that deflects harmful radiation, but the moon doesn't. Radiation hits the lunar surface and creates a secondary spray of particles that penetrate deeper than the primary radiation. Protection challenges. Future lunar inhabitants need multiple layers of protection. A lunar base needs at least 50 centimeters of lunar soil coverage to provide enough protection for regular operations. Solar storms demand stronger solutions. Calculations show that a chamber with about 10 meters of water would keep astronauts safe. Exploration activities create more complex problems. Astronauts in spacesuits receive about 60 microsieverts of radiation per hour. This exposure rate reaches 5 to 10 times higher than a transatlantic flight. Health risks for astronauts. Radiation exposure leads to several health issues. Without proper protection, astronauts risk immediate radiation sickness, long-term cancer risks, potential heart diseases, vision problems, and cataracts. Research shows radiation affects male and female astronauts differently. Women space travelers face higher risks of cardiovascular problems and cancer. Their vision remains less affected by space conditions, and their immune cells recover faster than men's. NASA's strict safety protocols limit astronaut career radiation exposure. These rules prevent increasing lifetime cancer mortality risk beyond 3%. A 25-year-old female astronaut could spend nearly 700 Earth days exploring the lunar surface before reaching this limit. Seismic activity and moonquakes. Scientists have found something unexpected about the moon. It's not the quiet world we thought it was. Years of seismic monitoring show that our closest neighbor in space actually rings like a bell. Types of lunar seismic events. Scientists have identified 4 main types of moonquakes. Deep moonquakes, 700 to 1200 kilometer depth, make up 55% of all recorded events. Shallow moonquakes, less than 200 kilometer depth, are rare at less than 1%, but pack the biggest punch. Thermal moonquakes happen due to temperature changes. Impact-related events occur when meteoroids hit the moon. These lunar tremors behave nothing like earthquakes. Earth's quakes last only seconds or minutes, but moonquakes can shake for hours. The moon releases nowhere near as much seismic energy as Earth, about 80 times less. Impact on future structures. These seismic events create real challenges for building future moon bases. The Apollo seismic network picked up between 600 and 3,000 moonquakes each year, with some reaching 5.7 on the Richter scale. The moon's weak gravity makes these tremors a bigger problem. Even mild shaking could make structures unstable or break equipment. Research shows that areas in permanent shadow, like the Shackleton crater, could see landslides from just a little seismic activity. Monitoring systems. Our knowledge of lunar seismology started with the Apollo passive seismic experiment, which gave us our first good look at the moon's internal structure. The network had 4 seismometers that ran on solar power, 3 long-period and 1 short-period vertical seismometer. Equipment to detect meteorite impacts and moonquakes. Scientists are now developing better monitoring tools. The Lunar Environment Monitoring Station, LEMs, shows how far we've come. This new system can work for up to 2 years on the moon, study the structure of the moon's crust and mantle, handle extreme temperature swings with new thermal protection. The Distributed Acoustic Sensing (DAS) technology looks promising too. A single fiber optic cable could provide thousands of monitoring points. This would help us detect and study moonquakes much better across the lunar surface. Temperature extremes and thermal cycling. Our lunar studies show that temperature remains one of the toughest challenges in moon exploration. The moon's thermal environment goes beyond anything we see on Earth, which makes it a vital factor when planning future missions. Day-night temperature variations. The lunar surface experiences remarkable temperature swings. Temperatures at the equator reach 127 degrees Celsius, 260 degrees Fahrenheit during the day, and drop to minus 173 degrees Celsius, minus 280 degrees Fahrenheit at night. These changes become more challenging because the moon's day-night cycle differs from Earth. Each lunar day and night lasts about 14 Earth days. Near the poles, in areas that never see sunlight, conditions become even more severe. Temperatures can fall below minus 238 degrees Celsius, minus 397 degrees Fahrenheit, making these spots some of the coldest places in our solar system. Impact on equipment. The harsh temperature cycles create several key problems for our equipment. Materials turn brittle at very low temperatures. Electronic systems stop working without special heating. Structural components wear out from constant expansion and contraction. Mechanical systems need ongoing temperature control. Regular gear systems need substantial heating to work in these conditions. A single lunar day-night cycle can expose equipment to temperature changes of nearly 500 degrees. Survival strategies. We're creating groundbreaking solutions to handle these thermal challenges. One major advance is metallic glass gears that work at temperatures as low as negative 173 degrees Celsius without extra heating. This technology could cut power needs for future missions substantially. Our team has designed advanced thermal management approaches for bigger systems. Thermal waddies, systems that use lunar soil store energy during daylight and release it at night. Heat exchange systems, new designs that use multiple mirrors and processed lunar soil for eco-friendly temperature control. Our latest radiator technology brings exciting possibilities. Self-morphing radiators adapt to both extreme heat and cold. They expand in hot conditions to release excess heat and contract during cold periods to keep warmth. Lunar habitats benefit from natural insulation. We learned that placing structures under about 1 meter of lunar regolith keeps a more stable temperature of around minus 53 degrees Celsius. While cold compared to Earth, this shows substantial improvement over surface conditions. Our loop heat pipe, LHP technology, creates systems that manage heat transfer with minimal power use. This proves vital for survival during long lunar nights. These systems keep critical equipment running within safe temperature ranges efficiently. Micrometeoroid bombardment. Our ongoing lunar surface monitoring has revealed one of the moon's enduring mysteries: a constant shower of micrometeoroids. Research shows about 33 tons of meteoritic material hits the moon's surface daily. This creates an ever-changing landscape that presents major challenges to future lunar missions. Frequency and impact. The moon faces an intense barrage of impacts. Measurements indicate 10 micrometeoroid strikes happen every second per square meter. These impacts become dangerous because of their incredible speed. Records show velocities from 3 to 70 kilometers per second, with impacts averaging 20 kilometers per second. Impact frequency changes with particle size. A tiny surface area of about 150 square meters gets hit by one micrometeoroid larger than 0.5 millimeters in diameter each year. Small impacts can be devastating. A single 0.5 millimeter projectile hitting at 13 kilometers per second creates a crater nearly 2 millimeters deep in aluminum structures. Surface degradation. These impacts change the lunar surface in several ways. Create new craters ranging from 10 to 140 feet in diameter. Generate over 47,000 surface changes called splotches. Overturn 99% of the surface material every 81,000 years. Produce secondary debris that poses additional risks. The Lunar Reconnaissance Orbiter camera's temporal pair analysis shows the actual cratering rate is about 30% higher than previous models predicted. This finding affects how we determine lunar features' age and plan future missions. Protection methods. Our research has helped develop several protective strategies for future lunar infrastructure. Regolith shielding. A 15.2 centimeter gap filled with lunar soil reduces penetration risk to less than 1 in 10,000 over a 2 to 5 year period. Multi-layer protection. Designs use lightweight materials like aluminum foil or nylon in tent-like structures. Advanced monitoring, new detection systems track and analyze impact events. The LumioCam now helps us measure impacts on the lunar far side with exceptional accuracy. This capability is vital to protect future lunar installations and understand the moon's mysterious impact patterns. Surface assets need designs that withstand impacts from particles moving at speeds up to 500 meters per second. This requirement forms the lifeblood of lunar infrastructure planning, especially in areas housing critical equipment or human occupants. South Pole-Aitken Basin mysteries. The South Pole-Aitken Basin, a massive impact crater hidden beneath the lunar surface, holds fascinating secrets about our moon's violent history. Scientists continue to uncover mysteries that reshape our understanding of lunar geology. Underground mass analysis. A massive underground structure beneath the basin has amazed researchers. The anomalous mass equals a metal deposit 5 times bigger than Hawaii's Big Island. This mysterious structure runs deeper than 300 kilometers and pushes down the basin floor by more than half a mile. NASA's Grail mission data revealed these key features of the underground anomaly. mass excess of at least 2.18 times 10 to the power of 18 kilograms, about 0.003% of Moon's total mass. Peak anomaly of at least 6 times 10 to the power of 6 kilograms per square meter. Location centered at approximately 200 degrees east, 62 degrees south. Potential hazards. The region presents several challenges to future exploration. The basin's complex geological environment needs careful planning. Recent studies suggest the impact created a more circular crater than scientists first thought, which changes what we know about debris distribution near the South Pole. This massive underground structure creates unique challenges: potential gravitational anomalies affecting landing operations, complex surface geology requiring specialized equipment, uncertain stability conditions for future structures, challenges in accessing and studying deep materials. Scientific significance. The basin stands as a cornerstone of lunar science. Scientists dated this remarkable structure between 4.32 and 4.33 billion years ago, about 120 million years older than previous estimates. This finding changes our view of the Moon's development. The basin's formation shaped early lunar development significantly. The impact dug up material from the Moon's lower crust and upper mantle. This gives scientists unique access to materials usually hidden deep below. Artemis mission astronauts might easily reach these ancient lunar materials that could explain how the Moon and our solar system formed. The Chandrayaan-3 mission's recent findings near the lunar South Pole support the theory about the impact's nature. Scientists found minerals that show impact debris from the mantle, which helps explain how this mysterious region formed. The South Pole-Aitken Basin teaches us more about the Moon's makeup and history every day. This giant crater stretches nearly 1,250 miles, 2,000 kilometers, making it the Moon's largest crater and one of the biggest known impact features in our solar system. Dust and regolith. Challenges. Lunar dust has emerged as one of our biggest challenges in Moon exploration. This fine powder, created over billions of years by meteorite impacts, threatens our equipment and astronauts' health in ways we never predicted. Mechanical wear issues. Our studies show that lunar dust particles destroy equipment at an alarming rate. These particles can score, stick to, and embed themselves into surfaces in tight spaces. This leads to early component wear or complete breakdown. The dust's abrasive properties vary based on where it comes from on the Moon, which makes the problem even more complex. The Apollo mission data paints a clear picture of how equipment breaks down. Brief exposure to lunar dust can cause obscured visors and clogged mechanisms, erosion of spacesuit layers, false instrument readings, thermal control system failures, seal deterioration. Health concerns. Medical studies have revealed scary health risks from lunar dust exposure. Tests on human lung and brain cells showed the dust killed 90% of the cells. The ultra-fine particles, smaller than 20 microns, about 0.00078 inches, pose serious health risks. Apollo missions taught us about immediate health effects. Astronauts dealt with burning eyes and decreased vision, respiratory irritation and cough, skin irritation, potential cardiovascular effects. These symptoms showed up after just short exposures during Apollo missions. Long-term lunar stays will need better solutions to these health risks. Mitigation strategies. We've created a layered plan to curb these challenges. Our dust mitigation strategy has 3 main parts: passive protection surface coatings that minimize dust adhesion, mechanical shielding technologies, work function matching coatings, active systems, electrodynamic dust shields, EDS magnetic filtration systems, compressed gas cleaning methods, operational procedures, dust airlocks or mud rooms, 2-stage cabin filtration, regular equipment maintenance protocols. Recent research shows great progress with the electrodynamic dust shield, EDS technology. It helps keep optical systems and thermal surfaces clean. New materials can now last up to 2,500 hours during surface activities, which beats Apollo-era equipment by a long shot. Brushing doesn't work well in vacuum conditions. The dust becomes easier to clean once equipment returns to pressurized areas because the atmosphere helps discharge its electrostatic properties. This finding led us to develop better cleaning methods for future lunar habitats. Future colonization risks. The latest research into lunar colonization shows there are complex challenges we need to solve before humans can live permanently on the moon. The moon's environment holds many mysteries, and we found that there was a need for groundbreaking engineering solutions and careful planning to create green practices for lunar settlements. Infrastructure challenges. The core elements needed for sustained lunar presence must have reliable infrastructure systems. A lunar foundation surface habitat would need space for up to 4 crew members during original surface stays. The vital infrastructure components must have advanced solar collection systems, lightweight fission power units, radiation shielding structures, specialized landing pads, waste disposal systems, storage facilities. Building launch and landing facilities creates unique problems. Large vehicles like Starship or Blue Moon would create massive craters if they land on unprepared lunar surfaces. New microwave sintering processes can convert lunar regolith into durable structures for landing pads and protective barriers. Resource management. The moon's resource management needs a delicate balance between Earth-supplied materials and in-situ resource utilization, ISRU. Mining and refining materials on-site could provide substantial advantages over Earth deliveries because of lower energy costs. The sort of thing I love is finding substantial ice deposits at the moon's North Pole. At least 600 million tons of relatively pure ice sheets, several meters thick. Water is vital because it helps in producing breathable oxygen, creating rocket fuel, supporting life support systems, enabling green practices. Transitioning to lunar-developed fuel through ISRU will propel development for long-term sustainability. Progress in developing closed-loop life support systems that can use lunar-derived resources looks promising. Emergency response planning safety assessments show that emergency response planning needs specialized solutions unique to the lunar environment. Emergency rescue operations must work for crew members who travel distances up to 1.24 miles, 2 kilometers away, and across slopes of up to 20 degrees during EVAs. Emergency protocols must help rescue an incapacitated crew member weighing up to 343 kilograms, including their suit. This requirement led to innovative rescue solutions that don't rely on lunar rovers. A new International Lunar Search and Rescue (SAR) organization, modeled after the International Submarine Escape and Rescue Liaison Office, is taking shape. The planning has sections for surface-to-surface communication systems, wireless ground infrastructure, orbiting relay satellites, emergency capabilities, systems interoperability protocols, multilingual emergency phraseology, and standardized procedures across different space agencies need immediate attention. Without proper interoperability between U.S. and other international moon programs, critical emergency response capabilities could fail. A full picture shows that successful lunar colonization needs solutions for multiple interconnected challenges. Original lunar missions will substantially shape our concept of operations. These missions will test and demonstrate vital systems before expanding human presence on the moon. The focus remains on developing technologies that will expand our capabilities and reduce lunar operations costs over time. Conclusion. Our detailed study of lunar mysteries shows the moon is a complex and challenging place for future human settlements. Years of research have helped us find many hazards that just need new answers before we can build permanent bases. The moon's ancient volcanic history and current seismic activity have created a changing surface with deep craters and big lava plains. Space radiation creates major risks that need strong protection systems to keep both equipment and humans safe. Our technology faces stress from extreme temperature changes. Tiny space rocks constantly hit the surface and put structures at risk. The South Pole-Aitken Basin is evidence of the moon's violent past. This area holds clues that could help us understand how our solar system formed. Lunar dust has become an unexpected but serious problem. Its sharp, electrically charged particles damage machines and threaten human health. These findings shape how we plan future moon colonies. A soaring wind depends on solving several connected challenges. from building reliable systems to handling resources and emergency plans. Our research keeps moving forward steadily to find ways that will support long-term human life on the moon. The moon's secrets push us to develop new technology and expand what we know. Every discovery helps us understand our cosmic neighbor better and shows us where we fit in space. What makes the moon such a challenging environment for human exploration? The moon presents numerous hazards, including extreme radiation exposure, severe temperature fluctuations, constant micrometeoroid bombardment, and the presence of abrasive lunar dust. These factors pose significant risks to both astronauts and equipment, requiring innovative solutions for protection and survival. Are there any active volcanoes on the moon? While there are no currently active volcanoes on the moon, recent evidence suggests volcanic activity occurred much more recently than previously thought. Discoveries from missions like Chang'e 5 have revealed volcanic deposits as young as 120 million years old, challenging our understanding of the moon's geological history. What is the South Pole-Aitken Basin, and why is it significant? The South Pole-Aitken Basin is the largest known impact crater on the moon, spanning nearly 1,250 miles. It's significant because it contains a massive underground structure that could provide insights into the moon's formation and early solar system history. The basin also offers potential access to ancient lunar materials, making it a prime target for future exploration.